right. Good afternoon, everyone, and welcome to the CCAT Student Poster Competition sponsored by ITS Michigan. My name is Debbie Bazina, and I'm the Managing Director for CCAT. Education and training and workforce development are central to the mission of CCAT. The Student Poster Competition allows us to have an impact on future transportation leaders as they prepare to enter the industry. In total, we received 19 submissions across 3 universities that were reviewed by our panel of judges. All these submissions are available for our audience to review on the CCAT website, and the link can be found in the chat box. Today, the top 4 students from the University of Illinois at Urbana-Champaign and the University of Michigan have been selected to present their research. Our judges represent a range of government and industry agencies. John Abraham is the Director of Traffic and Operations for Macomb County, Michigan, which boasts to be on the cutting edge of transportation technology with a robust communication system and an advanced traffic operations center. Barb Land is the Executive Director at the Square One Education Network, a Michigan-based nonprofit educational organization serving K-12 teachers and students. Anthony Magnan is the head of emerging vehicle technology for Verizon Wireless, integrating 5G use cases and requirements into future vehicle platforms and the Smart City Initiative. Danil Prokhorov is the head
Danil
of
Prokhorov. Yeah.
darn it, is the head of the Future Research Department at Toyota North American R&D and has been involved in research and planning for various intelligent technologies such as highly automated vehicles, AI, and other futuristic systems. Liz Pulver manages research programs for the Technology Research Division at State Farm. She collaborates with academic and industry partners and stakeholders to drive State Farm's role in the safe and sustainable deployment of connected and automated vehicles in the mobility ecosystem. And lastly, Rini Sharoni is the Senior Principal Engineer at Toyota's Collaborative Safety Research Center, working on active safety, ADAS collaboration, and crash data analysis. Thank you to all of our judges for joining us today and to ITS Michigan for their support. Our first student is Sachindra Dahal from the University of Illinois. Sachindra, you may begin.
Hello everyone, my name is Sachindra Dahal. I'm a PhD student at University of Illinois at Urbana-Champaign. I'm going to present about passive sensing of conductive concrete for vehicle lateral positioning. So connected autonomous vehicles have arrived in different shape, size, form with different promises. They provide increased driver and passenger safety, increased roadway capacity, improved mobility for elderly, disabled, and youth. And they also provide decrease in traffic congestion and fuel consumption. So to discuss about how CAVs work, they have 2 parts, the connected part and the automated part. So the automated part consists of sensing, planning, and acting. So the sensor senses the environment, then the machine learning algorithm or computer vision algorithms, they plan the path based on that, and the actuators would execute the command given by these algorithms. And again, there is the connected part, which consists of DSRC or cellular method to implement vehicle to everything communication, basically vehicle to infrastructure, and vehicle to pedestrian methods. But the problem is when we have adverse weather like snow, rain, or fog, the sensing part of the automated section, it gets affected. And also the current vehicle to infrastructure approach, it just focuses on roadside unit or traffic lights. So the biggest infrastructure, the road itself, is missing in action, basically. So to discuss about how the CAVs stay in lane, currently they use GPS as a primary sensor, which gets coordinate from satellite. But the problem is the error is around 20 feet while the lane is just 12 feet wide. So the vehicles also use camera using computer vision to find the lane markings and stay within the lane where the GPS tells it to. So basically it is sensor fusion of GPS, camera, LiDAR, existing maps. So using a redundant information to predict better is how they achieve this goal. But one big problem is improper lane marking. Not everywhere there is very good proper lane marking. And another problem is even if there is a proper lane marking, there is bad weather, which affects the camera. So lane markings are not visible, or signal of GPS is worsened. To put into context, 33 states receive more than 10 inches of snow annually. Or, for example, in February 2019, 60% of the US was covered in snow. So weather independence is needed for large-scale deployment of CAVs. So the question arises, are the roads smart enough right now? The answer is no, because they don't communicate with CAVs. So roadways can actually supplement the current CAV sensors to improve lateral positioning, even when the condition is bad or adverse. So how can we achieve that is by using passive sensing. We can create a repeatable electromagnetic signature, which is pretty unique and can be identified by the autonomous vehicle. And we can create those signals in the pavement by using construction materials that's commonly used in pavement industry, like steel fiber or steel slag aggregates. We don't have to use expensive or sensors or something that consumes power or needs a lot of wiring. So I'll discuss about the lab testing that is going here at UFI. So we use a sensor, which is induction-based eddy current method, and it creates an alternating magnetic field using a 10-inch diameter coil at 200 Hertz. So whenever a metal target is brought into this field, it induces an eddy current, which is detected by the sensor. So in our case, it is a steel fiber reinforced concrete. So how we test it is we prepare a slab. We have made a slab which is 18-inch wide, 18-inch in length, and 6-inch in height. And on the top of the middle surface, we have made a notch which is 1 inch by 1 inch, or 2 inch by 2 inch, or 3 inch by 3 inch in diameter. And what we do is we make an electromagnetic prism, or a concrete prism that has steel fiber in it, and we make those prism of the exact size and put it into this and do the testing. So we mount the coil on a motorized frame, and the sensor is driven at a fixed height above the slab, and it is moved at a constant speed to collect the data. And in addition to the normal surface condition, we also test it in a different adverse weather condition, which is created by having a plastic container, which is not electromagnetic, and having a 0.5 inch, 1 inch, and 2 inch of ice or water standing on the plastic container and with the testing. So I'll present some of the results that we get when we pass the coil on top of the slab transversely. So this is an example signature. So what we observe is, so there is this electromagnetic prism, and as we move the sensor above, the highest signal is achieved directly over the electromagnetic material. And as we move offset from that electromagnetic material, the signal drops out. So this is an example where we change the height of the coil, or the height of the sensor above the slab. And when we increase it from 5 to 6 to 7 inches, the signal decreases. So there are different factors that would attenuate the signal that we achieve. So to test that, what we did is we created different factors. One is sensor height, electromagnetic prism, steel fiber content in the electromagnetic prism, having water or ice on the surface. So we changed these parameters at 3 different signal attenuation level. So having a lowest signal attenuation gives us the best signal basically. And we increase each of these parameters and see how the signal deteriorates. So for example, this point is when the coil height is at 5 inches, steel prism size is 3 inch wide, and we have 1% of steel fiber without ice or water. We get this signal, and we just change each of these parameters and see how the signal attenuates. So what we observed is these 3 parameters, which are prism size, sensor height above the slab, and the fiber content, it attenuates the signal highest. And these are the factors that can be controlled during the design. We can say what size of prism we need in the road, at what heights can we implement or put the sensor in a vehicle, or what content of fiber we can put in the road. The factor of water, when we had 2 inches of water standing on the slab, it was still detected, it attenuated by 23%, but the signal was still detected. And when we put 2 inches of ice on the surface, we did not see any signal attenuation. That's because ice has a dielectric constant of 3, which is similar to that of air, versus water, which has 81. So in conclusion, we can strategically modify the pavement material to create electromagnetic signature that is repeatable and can be detected by CAVs. From our research, it was found that some of the highest signal attenuation parameters can be controlled in design process. The strong signal was still detected when the adverse conditions were present. And for the future, the roads can be designed not just for the physical properties, but also for the electromagnetic properties to help connected and autonomous vehicles. And I would like to thank CCAT for the funding for this project. And thank you, and I'm open for any questions.
Thanks. So we have about 5 minutes for questions. So first, I'd like to start with questions from the judges.
I have a quick question. I was just wondering what happens on pavement which is over, say, a bridge which is already metallic. It's a metallic truss.
All right. So over a metallic bridge, or for example, CRCP, I can show you a slide. I prepared a slide for that. So basically, when there are a lot of reinforcement present on a pavement, what happens is, as our research showed, that the coil height would highly affect the amount of signal. So although these signal would be highest, but we have a metallic signature on the surface, which would give us slightly higher. So when we look at the lateral profile, we would still get a higher signal at the location where we plan it to get.
Okay.
I had a question. My question, sorry.
Mhm.
My question is, so the sensor placement seems like it's important. Can you place the sensor, or are you placing the sensor to test so that the car can distinguish between individual lanes, or it's just plain distinguishing where is the road and where is not the road?
It is basically it is identifying where exactly the vehicle would be on a road laterally. So instead of just one sensor, we would have an array of sensors, and the sensor that reads the highest, which would, for example, if it is in the middle of the car, it would read the highest signal. We would know based on which sensor reads the highest value, we would know what part of the car is in the center of the lane, basically, if I answered the question.
Yes, I'm still a little confused how you are designing it. So yes, I understand that you can place multiple sensors and you will know, which sensor you're getting the signal from, but how would the car know where exactly are the sensors, the position of the sensors on the road?
So if we have, well, we don't have sensor on the road. The material on the road is always in the center of the lane of the road. So based on the sensor location in the vehicle
itself, the
itself,
sensors located on the vehicle, okay.
Yes. So based on that sensor location on the vehicle, it would know where it is getting the highest signal from the electromagnetic signature. And based on which sensor is reading the highest, it would know what part of the vehicle is at the center of the lane.
I see. Okay.
Mm-hmm.
So I'd like to ask a question about construction materials briefly, if you don't mind. So in a couple of different regions, especially here in the colder climates, there's been talk about going from steel rebar going into carbon fiber. Have you been able to, is this type of use case going to be applicable with carbon fiber rebar as pre and post tensioning, or will this completely change the way that the sensors interact with the materials?
For the carbon fiber rebar, we have not, or reinforcement, we have not tried those materials, but some of these can be also produced by infusing different metallic particles. So as long as the construction material is infused with certain metallic particles, it would detect that. So just using the traditional carbon fiber would not, I assume, provide the signal. But yeah, if it can be modified with infusing certain metallic particles, it would definitely be able to identify that.
Talking about the slag and introduction into slag into the concrete?
Yes.
Okay.
Or steel fiber.
No, understood. My second question is, and this may not be relevant now, but just something to think about is, what about overall costs? Introducing this into an already expensive evolution. I mean, what kind of cost can we expect into this type in a real world scenario?
So basically, these things can be done in steps. For example, wherever there is rehabilitation of a road, we can do it in an overlay type of thing. So I did the cost calculation. So if we are using 3 inch by 3 inch, for example, the size of the prism, and using 1% of steel fiber to construct 1 mile of road, it would be around $125, including the concrete material and the steel fiber for 1 mile of road, which is not as significant, but if we want to retrofit it actively, we might have to wait for the right time to do the pavement rehabilitation. That might be the ideal time to do this type of thing, rather than going and destroying or making grooves on the road and filling it. We can wait till the roads are ready for retrofitting, and we can do this with an overlay system. But by the calculation, it's around $125 per mile.
Great, thank you.
We have a question from Lecz from WCC. Any data on the signal attenuation effects of the mixture of water and salt/sand?
We have not done those right now, but we plan to do that. For this type of thing, we have a paper related to this exact thing that I would be happy to provide. But we have not done exactly with the salt and water, but we have done it with water and ice right now. But I've tested, although not for the paper, I've tested it, and it does not attenuate the signal significantly. It attenuates somewhat similar to how water does, because water has dielectric constant of 81, which is very high compared to having salt and water.
Great, thank you. I think that's all the time we have for questions. So we're going to move on to the next student, which is Xingmin Wang from University of Michigan.
Hello, everyone. I'm Xingmin Wang, a third-year PhD candidate from the University of Michigan, advanced by Mr. Henry Liu. Today, I will present the topic I present today is the data infrastructure for connected vehicle applications. So the data infrastructure we built is based on the Anabra Connected Vehicle Test Environment, which is short for AACVT project. And this project comes from the original safety pilot model deployment, which was started in 2012, and in 2015, the safety pilot model deployment project becomes the current AACVT project, which is still the largest operational real-world deployment of connected vehicles. And for the vehicle deployment, the AACVT project has totally installed over 2,500 vehicles, which were either equipped with the aftermarket safety devices or the vehicle awareness devices. And from the infrastructure side, the AACVT project has installed over 75 roadside units, including 69 production sites and 6 testing sites. And all the roadside units roadside units collect the basic safety message data and broadcast the signal phase and timing data at the same time. And the communication range between the vehicle and the roadside infrastructure is about 100 to 200 meters. And for the data contents, we have 2 main data sources. The first is the basic safety message data broadcast by the vehicles, which follows the SAE standard. And this message contains the real-time latitude, longitude, and time step and other and also other safety-related messages of the vehicles. And the other data source is the spec data, which is the signal phase and timing data. And this data is sent directly from the controller, and this data set contains all the signal phase and all the signal states of the intersection phases. And for the resolution and the transmission delay, both this data was sent for every 0.1 second, and the delay were within 1 second, which can definitely support the real-time applications. And based on this data collected from the AACVT project, we built a data infrastructure to process and visualize the raw data for the real-time connected vehicle applications. And basically, the data infrastructure contains 3 parts. The first is the data receiving parts, and the second is the data pre-processing, and the last is the upper layer applications. And for data processing, we have 2 different data sources. The first is spec data, and then is the BSM data. And both these data have to be decoded before it can be finally used. And from the other side, we also need offline map data, which is from the open source map, OpenStreetMap. And for the data processing, the most important part is to map the trajectory data to the road and associate with the signal phase and timing data. And with this match the trajectory data and the signal phase data, we are able to draw some aggregated time space diagram to evaluate the traffic signal control as well as the safety issues. And for the upper level applications, there are lots of potential applications that can be built based on this data infrastructure. And so far, we have drawn some plots to evaluate the efficiency of the intersection signal control. And also, we can also use this data to do some safety-related study. For example, to generate some safety measurements to evaluate the safety issues. And due to the limited time, I will skip some of the data pre-processing procedures, such as the denoising and the smoothing. And the most important part of the data processing is the trajectory data map matching. For the BSM data we collected, it's only collected near the roadside units. So the map matching here is to match the trajectory data to the corresponding movements. And here we use a hidden Macomb model to match the trajectory data. As shown in the left figure, both the movements shown by the blue lines and the trajectories shown by the red lines can be represented as a vector composed of series GPS points. And the xi here is the GPS point of the trajectory, and the di here is the distance between the trajectory point and the road movement. And the phi here is the angle between the vehicle trajectory and between the heading of the vehicle trajectory and the road movement. And for the hidden Macomb model, we consider 2 factors to do the map matching. The first is the distance between first is the state probability, which is the distance between the GPS point and the road movement. Here we assume that given a trajectory belongs to a road movement, the distance follows the Gaussian distribution. And the other side is the transition probability in the hidden Macomb model. Here we define this as the heading angle between the vehicle trajectory and the road movement. Basically, here we assume that the transition probability follows exponential distribution. With these two factors, we can calculate the total probability as the production of the state probability and the transition probability of all the trajectory points of a given trajectory, and then we can maximize the total probability to get the movement that this trajectory belongs to. And for this map matching problem, it can be efficiently solved using the dynamic programming algorithm. And here are the results for the trajectory data map matching. And each subplot stands for a movement of the intersection. The horizontal axis is longitude, and the vertical axis is latitude. The blue points and the dots are the road, and the red points are the matched trajectories. As we can see, using our algorithm, most of the trajectory points were matched to the road correctly. And combine the signal phase and timing data and the matched trajectory data, we can draw the aggregate time space diagram to evaluate the traffic intersection signal control. Since most of the traffic signals in the city of Ann Arbor are actuated or adaptive signal control, which means that the cycle lengths of different cycles are usually different. So here is what we do to draw the aggregated time space diagram. We have the trajectories of different cycles, and we can shift the trajectory in different cycles so that they share the same green start time. And finally, we can draw the aggregated time space diagram, which will be frequently used to evaluate the efficiency of the intersections. And to evaluate the traffic signal control, we also draw the stop delay scatters and the stop position scatters to evaluate the performance of the intersection signal control. So the left figure shows, given a trajectory data, how we can calculate its maximum stop position and also the total stop delay. And with this method, then we can plot each trajectory as a point to get the stop delay, stop position scatters and the stop delay scatters as shown by the two red figures. So the horizontal axis is the time of day when the vehicle traversing the intersection, and the vertical axis is the stop position and the stop delay accordingly. And based on these figures, we can easily evaluate the efficiency of the intersection signal control. And then I will give more examples. And this is we use 5 week states data from the Magnan and the Fuller Street located at Ann Arbor. And this intersection have 8 phases. And here is the aggregated time space diagram of the 8 movements. For movements, we can clearly see the departure shockwave since we have all the trajectory data have the same green start time. And these figures are the stop delay scatters. And from these scatters, we can clearly see the stop delay of the different movements of the intersection. For example, for the phase 5, if we draw a line, horizontal line as a cycle length, all the plots above the cycle length means that this vehicle did not pass the intersection within 1 cycle. This means that this intersection has suffers a lot from the oversaturation. We can, for the optimization, we can increase the cycle length to avoid the oversaturation to reduce the total delay of the vehicles. And for the stop position scatters, basically we can roughly see the queue length of the from this figure. For example, we can see from the phase 6, we can see a long queues over 140 meters, and this long queues would cause the very severe traffic congestion. It would cause spillover as an adjacent intersection, and also as well as the gridlock for the urban traffic network. And based on this evaluation and plots, we also develop a website which we usually call it AACVT lab website. And in this website, we can visualize all the plots and all the data. So can you see the slide? Can you see the website now?
Yes.
Okay. In this plot, as shown in this figure, all the red markers are the locations where the roadside units were installed, and all the blue points are the real-time trajectories. And this is exactly the 5 minutes from. There is only a 5 minutes lag from the real time, and all these blue dots are the real-time vehicles. And from this website, if we click on the markers, we can see the basic statistics of the, for example, of the specific intersection. For example, the number of vehicles passed by the intersection for different phases, also the average stop delay, average stop positions, and also the plots we mentioned before, including the stop delay scatters, the stop position, the time space diagram, and also the number of vehicles within the day. Okay. As we mentioned before, there are different applications that can be built based on these data infrastructures that were developed. For urban traffic mobility, we can use this data to traffic estimation and traffic signal control. Actually, this is what I have done all the time. And on the other side, we can use this data to do some safety measurement. For example, as far as I know, I'm very glad that this data set has support at least 2 projects. The first is to use this data to identify the aggressive drivers, and the other is project I know is to use this data to detect the dilemma zone, and also to furthermore to optimize the red and all red, the yellow and all red clearance time of the intersection. And thanks for listening. Basically, that's it.
Yes, I have a question. I'm trying to understand your whole overall process. So the cars which are equipped with the receiver for the connected vehicles, they are driving around and they're communicating with the infrastructure, and then the cars are sending to a server this data. Like, where is the raw data coming from, where going to where before you're doing the processing?
Okay, I'm sorry that I did not make this part clear, and I will try to explain it. So the first, the car equipped with the onboard unit can broadcast the basic safety message, and this will send this data will be sent to the roadside unit via the DSRC, and then the DSRC transfer the data via through the IPv4 to another city network, and then the data was forwarded to the server located at the arm tree, and then we can query the data through the UDP.
So what is the delay from when the car is sending the data to when it arrives at arm tree? And then what additional delay for processing?
Here is the delay. So the average delay for the basic safety message is about 0.3 seconds, which means that from the data was generated from the onboard unit until we receive it, the overall delay was about 0.3 seconds.
I see. So overall delay is around 0.3 seconds. Okay. Thank you.
Thanks.
So now currently, when we look at traffic signal performance measures, we talk about arrival on green. So is your system equipped to measure that so that we can do some automated signal performance measures?
Yeah. Actually, currently we use these 2 plots to evaluate the traffic signal control. The first is the stop delay scatters. Basically, we calculate the stop delay for each trajectory and plot this to these scatters. And for example, for this point, it means that a vehicle passed by the intersection at around 10 a.m. and the stop delay is over 2.5 minutes. And we can use these plots to evaluate the green split of the intersection. For example, if one of the phase has much larger delay than others, which this means that we should assign more green time to this phase. And we can use these plots to evaluate. We can definitely use these plots to evaluate the traffic signal control. And this is for the delay. And we also have the stop position scatters. This stands for the Q length of the different phase.
Now, you talked about applications for transportation engineering. How much penetration of vehicles? For example, do you need 20% connected vehicles in a traffic stream to come up to having useful data for these traffic applications?
Well, that's a very good question, and this is a research topic I have done since last year, and the intuition is that if we have different level of the penetration rate, we can do different levels of the traffic signal control. For example, if the penetration rate is too low, then maybe we can only use it for the fixed timing plan optimization. But with the higher penetration rate, we might be able to use this data to perform the real-time signal control. But for this data set, currently the penetration rate is less than 3%. So we might not be able to use this data for the real-time traffic, real-time signal optimization, but we might be able to use this data to optimize for example, a fixed timing plan or something like that. I think the penetration rate will be okay for the fixed timing plan optimization.
Okay. In order to give the same amount of time to all the presenters, we need to move on to our next presenter, but good questions. So next up is Xintao Yan.
Hello, everyone. This is Xintao Yan, a PhD student from University of Michigan. The topic I'm going to present today is a data-driven simulation of naturalistic driving environment for autonomous vehicle testing. So the first thing is that the AV testing and evaluation is very important for the AV development and deployment. The microscopic traffic simulation provides a testing platform for AV testing. The key idea is to test the AV safety performance in the simulation environment and make statistical comparisons with human driver performance. For example, here are two widely used microscopic traffic simulators, which is VSIM and Sumo. However, one key problem is that for this existing microscopic simulation platform is that the traffic behavior models lack the fidelity, and those cannot be directly used for AV testing purposes. The major goal for the existing behavior models is to evaluate the traffic efficiencies and emissions of the large-scale transportation systems. Therefore, the traffic behavior models were designed to roughly capture the normal behavior patterns, and usually only a small set of data is used for model calibration. However, for the AV testing purposes, the major goal is to evaluate the accident rate of the autonomous vehicle in a real-world traffic environment. And for human drivers, the accident rate is normally about 10 to the minus 6 to 10 to the minus 8 per mile from the naturalistic driving data. Therefore, for this rare events of the accidents, the traffic behavior models should be precise in both normal and rare conditions. Therefore, we can see there's a huge gap and need to be filled. We denote this problem as the naturalistic driving environment modeling problem. So we need to generate a model and generate a naturalistic driving environment, which is stochastic, naturalistic, and accident inclusive. So to generate such a realistic naturalistic driving environment, the behavior model of the vehicles needs to be distributionally consistent with the real-world traffic environment. This is a illustration figure. The axis here is the action given a state, for example, the acceleration in the free flow situation. And the y-axis here is the probability of different actions. So to generate such a realistic environment, the probabilistic distribution needs to not only capture the driving behavior in normal situations, but also in rare conditions. And to further extend this idea, we denote the state and action of vehicles as S and A. And the vehicle behavior model is actually a function. It's a mapping F from the state to action space. And the function F should be a stochastic function, and its distribution should be consistent with the real-world traffic environment. Therefore, we propose the framework of the data-driven naturalistic driving environment modeling. There are three steps. The first one is the naturalistic driving data collection and pre-processing. The naturalistic driving data, which is NDD, is very important because it records the actions of the behavior. It records the human driving behaviors when facing different situations, and this is very important if you want to construct a realistic environment. Here we use the NDD collected by the Armtree at the University of Michigan for this study, and the second step is the data-driven driving behavior modeling. From the NDD, we can classify the driving behaviors into different categories. For example, the car falling, lane changing, free flow, etc. And then we can get the empirical behavior models, empirical distributions of the behaviors. For example, here, this figure shows the longitudinal acceleration distribution in the free flow driving situations, given different speed of the ego vehicle. And however, due to the inevitably data noise and also the high dimensional nature of the human driving behaviors, simply use the empirical behavior models may result into bad results because the error would accumulate along the simulation. So therefore, we proposed optimization-based smoothing techniques to improve based on the empirical behavior models to match the empirical measurement distribution. Here, for example, we choose the velocity distribution, which is directly obtained from the NDD. We want to match the simulated velocity distribution of the simulation with the empirical velocity distribution from the real world. And then after the second step, we can construct the data-driven naturalistic driving environment with the data-driven initialization method as also proposed in this work to generate the entire simulation environment. Here is how we optimize the longitudinal behavior models. Due to the time limit, I won't go into the details of the optimization formulation, but the key idea is that we model the NDE as a Markov chain, and the convex optimization problem is formulated to optimize the longitudinal behavior model to reach a realistic NDE. And then to validate the performance of our methods, we collected trajectory data from our simulation and compared with the few widely used benchmark driving behavior models. The top two figures shows the velocity and spacing distribution collected from the simulation. The blue bar is the ground truth obtained from the naturalistic driving environment, which is the velocity distribution and the spacing distribution in the real world. And the yellow bar here is the simulated results. And the green bar is the initialization results, also from the given by our initialization method. And the bottom two figures shows the two widely used driving behavior models, which is the intelligent driver models and the Wiedemann models. These parameters of these models are calibrated from the naturalistic driving data from Virginia Tech and Shanghai. And notice that the Wiedemann model is actually the default car-following model for the vSim. And comparing this result, we can find our proposed method can significantly capture the stochasticity and also naturalistic of the human driving behaviors. And due to these two models lack the stochasticity and does not consider the distribution inconsistent with the real world driving environment measurement. So we can find the velocity distribution and spacing distribution of these benchmark methods are very dense and concentrated in certain interval rather than distributed naturally in this whole interval. And then to further validate our proposed NDE, we choose a AV model to test in this proposed environment. The AV under test we use use the IDM and the mobile models with calibrated parameters. And after about 25 million driving miles for the AV testing on highway, we can obtain the accident rate result as shown in this left figure. The axis here shows the number of tests, and the y-axis here shows the accident rate. We can find the estimated accident rate is about 2 times 10 to the minus 6 accident per mile, and it took about 9 times 10 to the power 7 test time to reach the estimation error. Estimation accuracy, which is we set as 20%, as shown in this figure. We can see after this point, the estimation results converge and within the 20% relative error. So you can find the proposed NDE can actually used for testing AV safety performance in such a for these rare events, which is accidents. And here also from the AV testing results, diverse accident cases can be generated. And also this kind of accident cases is very valuable, can provide information regarding to the AV and the test, and can be further used for AV performance improvement. Here I choose 2 examples, which is cut-in case and lane conflict case. The blue vehicle here is the AV under test, and the green vehicles in the videos is the background vehicle. So I will play this video. In this video, we can find the background vehicle is doing a cut-in maneuver. And because of the big difference of the relative speed, the autonomous vehicle tried to do an evasive lane changing maneuver, but because but it failed, so there's an accident happens here. And on the right cases is a lane conflict situation, where the autonomous vehicle and the background vehicle, this green one, is doing a lane changing maneuver simultaneously to a same target lane. And actually, these cases shows the drawbacks of the mobile model, because the mobile lane changing model only considers information of vehicles on the adjacent lane, so it ignores the vehicle's information on all other lanes. That's why the CAV tries to make a lane changing maneuver here, but the accident happens. So from these testing results and accident cases, we can learn more and have deeper understanding of the AV under test, and we can use these cases for further improvement to improve their safety performance.
Did you actually run the video? I didn't see any video.
Oh, okay. Sorry. Can you see the left? Yep. Okay. So this one is the cutting cases. Okay. So right one is the. Can you see this one?
Yep.
Okay. the blue and the green vehicles is doing a lane changing simultaneously to the same target lane. So there's an accident happens. And yeah, after these cases, we can find this information can help us to improve the AV afterwards. Sorry. Okay, this is our results. And finally, I would like to thank my advisor, Professor Hongyu Liu, for supervising and guiding this research. And I also want to acknowledge Dr. Shuofeng and Hao Weisun for collaborating in this research. And that's all. Thank you. Please feel free to ask if you have any questions.
Okay, I have a question. So you showed at the end that the estimation results has 20% error. So my question is, first, where are the errors coming from? So for example, which parameters are the most difficult to simulate that's introducing such a large error?
The relative error here is actually not coming from maybe the parameters, but because like if you want to estimate the accident rate of a autonomous vehicle, actually you need to do like infinite, let it run infinitely long, and we can the final result will converge. But apparently we cannot afford to run infinitely long distance, so we will choose when the accident rate is kind of not fluctuating and converge, we will think that is the acceptable estimated accident rate. So that's where's the error coming from.
Okay, so basically you're saying that if you keep running it much longer, then the error is going to go down, and at some point, many like simulation is going to converge to a very small error. Okay, next question is, when you're simulating and you showed some plot, it's still not clear how accurate of all the vehicle and driving models are with respect to the real car and the real driver situation. So what percentage of error you see there in the simulation?
That's a very good question. The idea we are using here is that the behavior model is directly come from the NDD data, and after optimization, then we choose a certain measurements to measure the error, whether this simulation produce a good environment comparing with the real world. So here we choose velocity and spacing, because the velocity of vehicles and the distance between each vehicle is very important and will affect AV performance in the testing, right? So we choose these parameters to see the simulated velocity distribution of vehicles and the simulated spacing distribution of the vehicles, how they are performed compared with the real world data. And also we compare with the benchmark methods. We can find comparing with these two benchmark methods, definitely, obviously our method is better, but of course, there's still room to improve to make it these blue bars and yellow bars more closer. But yes, that's like the further step we need to make this distribution much more closer.
Yes, do you have an idea of what you need to do to make the distribution be much closer?
Oh, yes. The reason why there's still a gap between here is because in the optimization step, we do some relaxation. So the model is not exactly accurate for the computational burden consideration. So maybe in the future, we will improve the optimization formulation to make it more accurate, to discard some of the relaxations. And another way is that we might try different methods, maybe the machine learning based methods, to substitute these optimization methods to further improve the model performance.
We will move on to the next presentation from Zhen Yang. So Zhen Yang, take it away.
Hello, everyone. My name is Zhen. I'm a fourth-year PhD candidate in University of Michigan, advised by Dr. Henry Liu. Today, I'm going to talk about the integrated traffic signal and vehicle trajectory control in a mixed traffic condition. I think most of you have heard of connected and automated vehicles. They can communicate with other systems by V2X technology, sense the environment, and perform specific driving tasks with automation. Here, I give you two examples of connected or automated vehicles in University of Michigan. The first one is an M-Bus, which is a connected vehicle. The second one is a Navia shuttle running in M-City, which is automated vehicles. The current existing solutions to IDCAV, say SAE level 3 or higher, require multiple expensive onboard sensors. So if we look at the automated vehicle of Google, you can see that it has a LiDAR, it has radar, cameras, all different kind of expensive onboard sensors. It also requires complicated trajectory planning and vehicle control algorithms, which bring a challenge in real-world implementation, especially in urban traffic. One way to address this problem is to have the smart infrastructure. So this table is provided by researchers in Europe. So they define the infrastructure level. With the lowest level, we have the conventional infrastructure. And when we improve the smart infrastructure level, we can have the map information support to CAV, we have the dynamic information, say the weather condition, or we may provide cooperative perception so the smart infrastructure can perceive the traffic situation and provide those perception to CAVs. And finally, we have the cooperative driving smart infrastructure, which can provide support to CAVs and manage all vehicles in mixed traffic conditions. So the key research question is that whether we can improve the smart infrastructure level to have lower requirement for CAV level. That's the reason why I proposed this cooperative driving framework, which mainly includes the two parts, the CAV module and infrastructure module. So we consider a mixed traffic condition in which we have the connected and automated vehicles. So those vehicles can broadcast their basic safety message, and they can also be controlled by some specific algorithm. We also have connected vehicles which are driven by human beings, but they can also broadcast their information. And finally, we have the regular vehicles, which is driven by human beings. They do not have any connectivity or automation. So for the connected vehicles, we consider the cooperation between CAVs. So we consider, so when several CAVs are close to each other, they can formulate a peloton. The peloton may split. And also for the leading vehicle of the peloton, it need to plan its own trajectory for the, it need to plan the trajectory for the whole peloton, whether the peloton need to stop, speed up, cruise, or slow down. The main functionality of the smart infrastructure is a signal optimization, which optimizes the time of arrival for each CAV at the stop bar and will be sent as a guidance to each CAV. So let's go to the details of the CAV module. We define 5 CAV control states: free flow state, intelligent follow, optimized control, launch, and stop state. So in this figure, we have the blue vehicle and the red vehicle as CAVs, and the black vehicle here is a regular vehicle. So here is actually the intersection. Before these 3 CAV enter the communication range, they are under the free flow state. So after they enter the communication range, the leading vehicle of the peloton will switch to optimized control state, and the following vehicle will switch to intelligent follow state. The leading vehicle, the blue vehicle, need to decide whether this peloton need to accelerate, cruise, decelerate, or stop at this intersection. So at this scenario, since the traffic signal is red, all those 3 vehicles just stop at this intersection. And when the signal turns to green, these 3 CAVs will switch to launch state and pass this intersection. After they pass the intersection, they will switch back to free flow state. I define a CAV's control state transition diagram. Due to a time limitation, I cannot go to the details of this transition diagram, but I want to mention that by using this diagram, we are able to capture the pelotoning behavior, say 2 pelotons merge into 1 peloton, or a peloton break into 2 pelotons. Next is the infrastructure module. The first functionality is a queuing prediction. Basically, all the vehicles are sorted based on the distance to the stop bar. For connected vehicle or connected and automated vehicles, we can use their basic safety message to get the distance to the stop bar. For regular vehicles, we use an entrance loop detector to estimate their distance to stop bar. After that, they are searched successively to determine whether a vehicle will stop. With queuing prediction, we are able to provide the green window information for a CAV to say whether it can pass this intersection. Another very important functionality of the smart infrastructure is the integrated optimization. The objective is to minimize the total delay of all vehicles. And the decision variables are the signal timing plan and also the time of arrival of each CAV. Notice that we do not optimize the detailed trajectory, CAV trajectory at the smart infrastructure. The detailed CAV trajectory is solved in the CAV module. In this way, we reduce the computational burden at the smart infrastructure. So here is the mixed integer linear programming we proposed for the signal optimization. The objective is to minimize the total delay of all vehicles approaching this intersection. So the first constraint is how do we calculate such delay? And we also have a group of signal constraints which represent this ring barrier diagram. We have the time of arrival constraints in general, which determine whether a vehicle will stop or not. And also we have the CACC specific time of arrival constraints, which determine whether Platon will split or not. Here is the simulation analysis. Let's first take a look at the right figure. So here is the simulation framework. The simulation is conducted in vSim, which has the signal controller to control the traffic signal. We have different kinds of CV and connectee and CV and RV. As I just mentioned, in the CV module, we have the speed profile generation. In the infrastructure module, we have the queuing profile prediction and signal optimization. So after the signal optimization, the optimized signal timing plan will be sent to signal controller, and the arrival time will be sent to CV module to plan its trajectory. After the simulation, we'll use the post-analysis module to get the fuel consumption and emission. So we use the intersection of Plymouth Road and Murphy Avenue in Ann Arbor, Michigan. The baseline we have is actuated signal control. And basically, we conducted two groups of experiments with the first one is with CAV and CV. The second one is with CV and RV, and under different penetration rates. So here is the results of the first group, CAV and CV. So we give you the performance of the mobility in terms of total vehicle delay and number of stops, and also give you the performance of the fuel consumption in terms of CO2 emission and energy consumption. So you can see that as we increase the penetration rate of CAV, we can have better and better performance in both mobility and fuel consumption. The second group is with CAV and RV. In general, the performance is still similar. When we have more penetration, we have more CAV, we can have better performance in terms of mobility and fuel consumption. There's just one thing for the number of stops. As you can see, if we increase the penetration rate, the performance goes worse a little bit and then goes better. The reason why we have such performance is that with regular vehicle, we cannot estimate the queue length very accurate. So that actually leads to a bad performance when we have more CAV. So in the conclusion, I proposed a cooperative driving framework in a mixed traffic condition of regular vehicles, connected vehicles, and connected automated vehicles. At the CAV module, we proposed a CAV control state transition diagram for different operating modes. At the infrastructure module, we optimized the traffic signal and also the CAV time of arrival with a mixed integer linear programming problem. The simulation results of a signalized intersection shows the benefit of mobility and fuel consumption, and the delay reduction can be as high as 18.7% on the high penetration rate of CAVs. Notice that we also extend this work to a traffic corridor in which we consider the coordination between different intersections. Due to time limit, I cannot present that work here. And that's all I have. Thank you.
Maybe I'll ask you about the definition of connected vehicles as opposed to connected and automated.
Yeah, so for the connected vehicles, they are driven by human beings, but they can provide basic safety message through the onboard unit. For connected and automated vehicles, they are not only provide such information through connectivity, but they are also controlled by some specific autonomous driving trajectory planning algorithm.
Thank you.
Yeah, thank you.
Yes, I have a question. You said you tested this on some fuel economy and mobility. Can you kind of, not the fuel side, but the mobility side, can you show what kind of benefit you saw from the mobility aspect? What is it?
Yeah, so for the mobility side, you can see that as we, so this two figures shows the total vehicle delay and number of stops when we have different penetration rate of CAVs. So as we increase the penetration rate of CAVs, the total vehicle delay and number of stops decrease. So that's the mobility performance.
I see. So that when you said the total vehicle delay, the total vehicle delay in driving time?
Oh, yes, yes, exactly.
Yeah, okay.
Yeah.
Driving time and ourselves. And did you look into any kind of safety aspect? So while you're optimizing these other things, is there anything on the safety side that's getting disadvantaged, or that safety is always maintained while you're doing these things?
Yeah, that's a very good point. So actually, due to time limitation, I'm not able to mention that, but we do, when we design the CAV trajectory planning algorithm, we do consider that they have the collision avoidance avoid collision with other cities. Yes. Yeah. Thank you for your question. That's a good question.
Thank you.
Thank you.
Okay, so at this time, we'll let the judges go to their other meeting to deliberate and make their decisions. While that is happening, I'd like to thank our students for your wonderful presentations. And we'd like to bring Al Lecz to discuss the student outreach efforts here at CCAT. Al Lecz is the director of the Advanced Transportation Center at Washtenaw Community College, a consortium member of CCAT. In this role, Al works collaboratively with credit and non-credit administrators and faculty to provide industry leadership related to training, programming, and other educational services.
All right, so I wanted to talk about outreach, and specifically as we really address students, but outreach in general. In the CCAT grant, this has become one of our major contributions to the grant. In terms of outreach, which I will go through here shortly. Many of the areas of outreach have to do with community engagements, student forums, business and employer events, conferences and regional events, tours and hosted events at Washtenaw Community College, and media and news. In the community engagements, and this one just happened in September 25th, actually, the Ann Arbor Spark Mobility Rule, which used to be on the streets of the downtown Ann Arbor this year because of COVID, had to go virtual. And what Ann Arbor Spark did was provide through Russell Video a chance to film the technologies that we would normally be displaying and the outreach that we would provide to interested community persons, who wanted to know more about the technologies or the programs driving the technologies. And so we were able to, we have this Polaris slingshot at the college, which has a number of technologies in it. It has DSRC for V2X communication. It has a number of LiDAR and cameras, sensors. It also has manufacturing implications in carbon fiber lightweighting and so forth. So we were able to display that through the Ann Arbor Spark event as part of a virtual explanation. But again, it is the outreach of the programs and the technologies that are being developed and delivered to students across the region. We've held a student forum in February before COVID restrictions occurred. And these had to be 2 students in our automotive technologies. They're learning about the sensors and the V2X communications and so forth. They're learning the automotive integrated technologies that are being implemented in products in the industry. And in this case, it was students talking to students. This was held in our library. And these 2 students from the automotive program, the automotive technologies program, came to present and answer questions to other students who really had no knowledge about the program or may have been contemplating, what is this, and how would it apply to me? And the students did a great job of explaining how they became interested in mobility type careers, and then answered questions from students. And other activities like business and employer events, this was a big one. Actually, this was a combination of IEEE and AutoSense organizations developing a conference to talk about all the sensors that are being used both in the infrastructure and in the vehicles, and how the sensors are being developed by their industry, if you will. And again, it gave a great opportunity for us. We're actually adjacent to the American Center for Mobility exhibit. And together we were kind of swapping, again, how the technologies can be really important in the emerging occupations that are coming. And again, we had a chance to do that at the Michigan Science Center in downtown Detroit. and it was a great conference, but lots of businesses there, the tier 1 suppliers of the sensors going into all the vehicles and the infrastructure. And here again, this was at the American Center for Mobility, and again they had an open house late last October. And what you can see is a group of students that came in the open house who wanted to sit and feel and understand what are all the technologies that are going into vehicles. And this was a great opportunity for us to explain to these students really what's going on in the emerging industries of mobility. And again, a great opportunity, and very inquisitive students that really wanted to understand what are you developing, and what's an opportunity for me in this field. And that was a great opportunity for us, and we thank the American Center for Mobility for that opportunity. And then we hosted a webinar. Well, it was a forum by the University of Michigan Society of Women Engineers, SWE, at the college. And we had some great guest speakers: Carla Balo from CAR, Mary Lynn from Umtree, and some others. And again, it was really a lecture about the future of mobility. And there were some great presentations to a combination of students and instructors and some parents. And that combination was opportune really to help instill an understanding of what are the emerging technologies and the emerging occupations. So these types of events are really powerful outreach events. And we at WCC typically go up to Traverse City every August for the Center for Automotive Research Management briefing seminars. And it's a great opportunity. There's usually 900 attendees. Most of them are companies, major and tier 1 minors. And it's a great chance. We typically bring students and instructors to really interact with the businesses. In this case, the center person there is Glenn Stevens from Mish Auto, really, who was being interviewed by John McElroy of WWJ, again, about his experiences and his information. But he happened to pick our exhibit, our WCC Advanced Transportation exhibit, and emailed me this photo, said, "I picked your exhibit for my interview." So he thanked us. But again, it's another example where this outreach and the connectivity between partners is so important to really broadcast what's going on in the industry and what are the opportunities. And we had, again, there's some things that WC hosted that were outreach examples. We had a Smart Cities Symposium, and a vice president from Ford Motor Company really talked about smart cities and where Ford Motor Company is going with that. The Umtree CCAT second annual global symposium, we hosted that. And again, it was a great opportunity for 3 of our students who are looking at this career field to be on one of the panels. And again, these are examples where we're speaking to the public at large, and our students are involved. And one of our great partners is Square One Education Network. And again, they've done so much over the last several years to instill an awareness in the middle and high school populations, both students and teachers. And they have these hands-on projects and use the academic year to develop the projects. And then in May, at the end, nearly the end of the school year, to hold a competition event. It's been held at M City, and it's currently being held at Kettering University. But a great opportunity for students to really get involved with obviously the control systems in automated vehicles. Their vehicles need to be lightweight, so they're learning material, how to handle lightweight materials. And by the way, the teachers get continuing education units when they're in these workshops for the time they're spending, really learning some of these advanced technologies, and to give them insights into, what's going on in the industry, what's emerging and what's being developed. And we also have a unique area of outreach to disadvantaged middle and high school students who typically cannot get to a forum like a symposium, and they typically do not get the kinds of attention, if you will, and we reach out to these people in Eastern Ypsilanti area and Willow Run to really bring to them some awareness training in computer programming or intelligent vehicle concepts that Square One offers. And here's some photos again of the middle and high school events in the Square One workshops. This upper right one is one of the workshops that we held at the school recently. And again, you can see the combinations of students and teachers working on their projects. And this was a competition event at M-City for a student team in past years with some of us there guiding them. Last year's Kettering event was really fun, if you will, in terms of we brought a repair trailer filled with welders and machining tools, soldering guns, and all kinds of things, because we knew that their vehicles are either going to break down or they'll need some sort of repair. And by the way, that's where the learning is for these students. They're getting so much knowledge from repairing a vehicle that breaks down, and believe it or not. So we had a lot of fun with it. This picture on the right, again, our instructors were coaching the students. They had to make some welds for safety reason to protect the backlash of their heads. And our instructor coached these students to make the welds and qualify their vehicles for the remainder of the competition. So again, just the engagement, the outreach that's going on with students and teachers and parents is really enormous momentum builders for this area. Other areas where outreach happens, we typically attend the North American International Auto Show. This was our exhibit in 2019. Again, we took our Polaris slingshot with its technologies, to the auto show. And again, Planet M, the state is involved, sponsoring us and many others, to display the technologies and answer the questions from so many of the public that turn out to be parents of students. And again, we provide information about, what programs to get into to kind of follow their interests. And one of the major areas that WCC is involved in is obviously in automotive cybersecurity. And we had this workbench, which has been a very popular hit both at the North American International Auto Show and other places. And the instructors are so focused and so dedicated to this emerging field. We've had our exhibits at so many different places. And one of them was the My Career Quest Southeast Michigan, managed by the Oakland County, Michigan Works Agency. Last November, there were over 9,000 students from Southeast Michigan high schools that attended that event, and they came through. I think I have a picture of it here. They came through there and they saw these exhibits of our technologies, so that we could answer their questions about what is this about? How does this fit into a career? And we could answer questions like that. So the other thing we've done, obviously, in terms of workforce development and so much of the online training that's happening today, is we're offering much of our intelligent transportation workforce modules through the World Education Network, which expands the outreach tremendously across the country and even beyond in terms of global. And we have presented, the U.S. Department of Transportation has a VOLPI ITS America Professional Capacity Building Workshop, and they bring colleges in, and we've been involved for a couple of years now to really display and promote and present our programs and how that fits into the skill gaps and the occupational pathways, if you will, for transportation technologists who are implementing many of the technologies that we heard earlier in this broadcast. And obviously the infrastructure needs technicians to manage obviously these roadside units and the signal phasing and all the rest of the control systems that are being proposed to be implemented. And so that's been a great opportunity, again, where we promote both our collaboration with UMTRI and the CCAT grant, and obviously things that we're developing at the workforce level. We have instructors that are constantly going and presenting at the Auto ISIC information sharing and summits that are held every year on automotive cybersecurity. And again, hosting high school students, many of them that are really brought there by the Square One Education Network to observe and understand the technologies like automotive cybersecurity. So, here's again, to kind of round this out and finish it up here, there's our cybersecurity. We have a cybersecurity club, if you will, that's been going to a lot of the national events and competing. And our instructor, again, here she is talking to many students at the My Career Quest Southeast about automotive cybersecurity with our workbench. And again, we take students and deans and others to the car MBS, and this was a picture a couple years back of some students and some administrators ready to meet companies and to understand and help us promote programs with this type of outreach. So that's really the end of it, to give you some chance to see what kinds of outreach activities we're involved with on behalf of the CCAT partners and Washtenaw Community College. So I'll end it right there.
Okay, so we're ready to announce after much deliberation. And, there was, all the presentations were fantastic. That was one of the, I'm going to say, takeaways of the judging. And it just took us a little while to come to the conclusion, because they were all so fantastic. And I just can't stress that I just can't stress it enough. One thing that the judges were saying is that all of these are such pertinent topics of, the work that they're doing or the work that they're interested in. So with no further ado, first I want to thank you all for, first I want to thank Al for engaging presentation on CCAT student outreach efforts. And we are pleased to announce that the judges have made their final decision and that the 2 awards will be granted today. So we want to thank all of the students that participated in this competition, and you should be extremely proud of all the remarkable work and accomplishments that you've made. The recipient of our runner-up award of $500 is Zhen Yang, so congratulations. And the recipient of our first place award, oh, whoops, I'm doing the wrong amounts. It was $750, yay. And the recipient of our first place award of $1,000 is Xintao Yan. So thank you so much and congratulations. Just a little bit of logistics is we have to mail the checks to you. So we'll be taking care of that after the presentation. But congratulations again. And I want to also thank ITS Michigan for sponsoring the event.